Hello, welcome to my channel. So in this circuit analysis video, I'm gonna derive the circuit response of the source-free parallelly connected RLC circuit. In my previous video, I derived the circuit response of the series source-free RLC circuit in both time domain and frequency domain. And now in this video I'm gonna derive the circuit response of this parallel RLC circuit, which is source free, in time domain, and then I am gonna analyze this circuit and find the response in frequency domain. So let's get started. So because I have found the circuit response of a series RLC circuit, which is generally a current response, the loop current. So because I know what the response of a series RLC circuit is, finding the circuit response of a parallel RLC circuit automatically becomes very easy and intuitive. But I can write you down the expression of the circuit response for this circuit, but I'm not gonna do that. I'm gonna derive it and mathematically prove the relationship to you. So basically the main response, which is voltage, it will have all the components same as it was in the circuit response, which is current in case of series RLC circuit. So and by the way, the parallel RLC circuit is an electrical dual of the series RLC circuit. In my later videos I will discuss what a dual is, what a dual pair is. So wait for that. Let's get started in this video. So in time domain analysis, I'm gonna apply KCL at node A here, and I have assumed current direction for the three node currents, so or branch current. So at node A by KCL so by KCL is IL plus IR plus IC equals 0. So, and I have assumed the reference node this point, this common point. So you can see how the equation goes. So by KCL, IL, current through the inductor, current through the resistor, and current through the capacitor, all combined is equal to 0. And there in the right hand side is 0 because there is no input. So current through the inductor is 1 by L integration Vt dt plus Vt by R, current through the inductor, and current through the capacitor is C d by dt Vt. So far so good. So now let me assume that differentiation is d with respect to time, obviously, and integration is 1 by d. So d is linear differential operator. So because this is an LTI system, the components are linear. This system for electrical circuits are also systems. This LTI system will generate linear differential equation with constant coefficients, where the constants are L, R and C. So without a doubt I can apply some special operators. So one of the special operator is the linear differential operator, which only acts upon the linear differential equation with constant coefficients, and I can use direct formulas which will make my calculations more easy. Okay, so now what I'm gonna do is I'm gonna take take common. So common C by D. So what will happen is this part will be D squared plus 1 by RC 1 by RCD plus 1 by LC. So this is looking like a more standardized form and equals to 0. Okay, so this is the second order linear differential equation with constant coefficients, and I have to solve this linear differential equation to get the circuit response of this source free parallel RLC circuit. Here this differential equation is an homogeneous equation. There is no input. Okay, so the right hand side is 0. If you know that the general solution or complete solution of a differential equation has two parts, one is complementary solution and the other is particular integral. So because the system has no input, there is no particular integral, and as a result of that, the system or this circuit has no steady state response. In terms of system response, this complementary solution is the transient response of a system. So we are only gonna find transient response for the source free circuit. So to find this complementary solution, we have to solve the characteristic equation of the system, in this case for this circuit. So we know that characteristic equation is the internal structure or internal dynamics of the system itself. So this is the characteristic equation of the LTI system parallel RLC circuit. In mathematical terms, this is also called the auxiliary equation. So now this looks like a second order polynomial. So I'm gonna straight use the formula for finding root of second order polynomial or the quadratic roots. D1 2. So as I did before, I'm gonna apply the formula here also, as I did in my series RLC source free response video. So by the formula minus b, which is 1 by RC, so minus 1 by RC plus minus root over 1 by RC. So here at this point I'm going to define some very important terms which are essential for understanding the response of the RLC circuit in particular. Okay, so one of the terms, as I defined for the series RLC circuit in my previous video, one of the important term is damping factor. Okay, this is defined like this because of it's convenient. Okay, and undamped omega n, I have defined this before in my previous videos, which is 1 by root over LC. New and One of the most important terms is damped natural frequency. I have defined this in my series RLC circuit response video. Omega n square minus psi or zeta square. So these are the three terms. So I'm going to substitute these for these values, and what we're going to get is a more understandable, less complex form of the roots. So here, if I just take it like this, so these two and these twos will cut out if I take the common, so leaving behind psi plus minus psi of zeta square minus omega n square. These are the two roots of the second order polynomial or the characteristic equation. Now we're gonna find the complementary solution. Complementary solution is, so complementary solution is also called the transient response of a system, of LTI system. So VTR is C1 e to the power lambda 1 t plus C2 e to the power lambda 2 t. So lambda 1 and lambda 2 are eigenvalues. So the roots of the characteristic equations are also called eigenvalues. Okay, so d1 d2 can also be generated by lambda 1 lambda 2. So if I just here, so break, if I just break this, so if I take the exponential psi minus psi t common out from the two, so it will leave us with c1 e to the power j omega dt plus c2 to the power minus j omega dt. So far so good. By Euler's formula we can express this term in terms of sines and cosines. So now to the power minus psi or zeta, so if I take c1 c2, so c3 cos omega dt, if I take cos as common, and c4 sin omega dt. So c4 is j c1 minus c2. Okay, here, so this is the complementary solution of the RLC circuit, and there is no particular integral in this case because the system is source free. Okay, so all we have to do now is find the arbitrary constants, and that will be it. So I'm gonna so how can we get the arbitrary constants? So we can get the arbitrary constants from the assumptions I have made for this system or for the circuit, that the initial current through the inductor and initial voltage across the capacitor. So I can use these assumptions, the boundary values, to get the arbitrary constants, these two, C3 and C4. So the complete response is Vt equals Vtr plus 0. Remind you, this is a source free system, there's no input, so there is no particular integral for this differential equation and for the solution, and as a result this system has no steady state response, it only has the transient response. So the solution is, so this is the circuit response. All we have to do is we have to find the arbitrary constant. So I have assumed, say at t equals 0, voltage across the capacitor is VO. So VT equals VT equals 0 is VO. So which will give me C3 equals the initial voltage. So we have found our first arbitrary constant. Now we have to find the second arbitrary constant. So to find second arbitrary constant, I have to take in the consideration this assumption that in the car at t equals 0, the current through the inductor is IO. So current through the inductor is 1 by L integration the node voltage dt. So here comes the problem, because this is an integration, and the integral Vt has two parts. So these two parts which are in multiplication form, so the calculation will be a bit long. So regardless, I will do it, no problem. So first let me take this integral because I, so this is, so voltage is the node voltage is the response, actual response of this circuit for this case, the parallel connected case. So so for this integration the uv dx formula would apply. So let me assume, so let u equals c3 cos omega dt plus c4 sin omega dt, and v equals exponential, the damping term. So this, and now we're gonna use the formula integration uv dx. Okay, so I have done the integration. So this is very long, and I haven't done any mistakes. So long story short, I have applied this formula. When I substituted for the assumed terms, so u is this whole term c3 cos omega dt plus c4 sin omega dt, and v is, I have assumed exponential e to the power minus psi or zeta t, and because the terms are functions of time, the differential which is dx will be converted into dt. So this I have I have just applied the formula and did the calculation, did integration. So you can see, so if you want to understand, pause this video and watch this calculation from top to bottom, from start to finish, attentively, and try to do it yourself. So basically what I am left with is this. I'm just gonna take this value, this relation, and apply this in the current equation of the inductor, and find the C4. Okay, so now current through the inductor is 1 by L I is the integral I have assumed. So now 1 by L, so if I take this term to the right hand side, it will look like psi or zeta, the damping factor is square, psi square plus omega d squared. Now, so we are at the final stage of our derivation for the circuit response of the parallel RLC circuit. Now I have assumed that IT equals 0, there was initial current through the inductor, which is IO. Now 1 by L psi square, if I break this omega d, which will be, so psi square plus omega n square minus psi square, so this will cut out, minus C3 dot 0. Now 1 by L psi square omega n squared, and here minus 1 by psi C3 minus omega d. Okay, so C3 is initial voltage across the capacitor. Okay, so this is psi by omega n square is 1 by LC, so LC will, okay, so this VO, also there is omega n square, so omega n square will be C4. So this is basically minus omega d C. C4 is initial current plus psi C, the damping factor, VO. So this is our arbitrary constant. So now we have found all our arbitrary constants. So we have found our arbitrary constant C3. C3 is the initial voltage across the capacitor, and C4, after that long integration, that long calculation, I have found that the C4 is minus IO by, which is initial current through the inductor, IO by omega d. C is capacitance, plus psi is damping factor, omega by omega d. Omega d is the damped natural frequency, VO in the brackets. So I have just substituted for the arbitrary constants here. Then this the complementary solution looks like this, and here I have just rearranged the value, the terms, and this is what it looks like. This is the complete response of the source free parallelly connected RLC circuit. So remind you that there is no particular integral, so there is no steady state response. This is only the transient response of the circuit. So it looks almost like the same as the response we found, or I found, in the series source free RLC circuit response. So this tells us that the parallel RLC circuit is an electrical duo of the series RLC circuit. This is it. This is the response of the source free parallelly connected RLC circuit. I hope you understood my explanation and my calculations. If I have made any mistakes, you can tell me. I will immediately try to write the mistakes I have done. So that's it. And here the damping factor in this case is 1 by 2 RC, and omega n is natural undamped natural frequency. So omega n is undamped natural frequency, which is 1 by root over LC, and omega d is damped natural frequency of the circuit or of the system, which is root over omega n square minus psi square or zeta square.